students, myself Dilip Adani, Assistant Professor at LG Institute of Engineering and Technology. The name of the unit is Ordinary Differential Equation of Higher Order, and today's topic is Euler-Cauchy equations. So let's start. First of all, I will make you understand what is Euler-Cauchy equation. A differential equation of the form a0 x raised to n, nth derivative of y with respect to x, plus a1 x raised to n minus 1, n minus 1 derivative of y with respect to x, plus a2 x raised to n minus 2, n minus 2 derivative of y with respect to x, and so on, plus a and y equals to q of x, where a0, a1, a2 up to an are constants, is called Euler-Cauchy equation. Now to solve this Euler-Cauchy equation, let x equals to e raised to z. Now differentiating this equation with respect to x, derivative of x is 1, derivative of e raised to z is e raised to z, and as you can see that z is a function of x, so we have dz by dx. So from this equation we have dz by dx, that is equals to 1 upon e raised to z, and this is equals to, see, e raised to z equals to x, so this is equals to 1 upon x. So indirectly we have dz by dx equals to 1 upon x. So this is equation number 1. Now if we will replace x by e raised to z in equation number 1, it will become y in terms of z. So dy by dx, y is a function of z, so that is dy by dz, and we have taken x equals to e raised to z, and z is a function of x, so we will write down dz by dx. Therefore dy by dx, that is equals to dy by dz, dz by dx, that is 1 upon x. Now multiplying both sides by x, so we have x dy by dx, that is equals to dy by dz. So we have x dy, that is equals to dy, where this d is d by dz, and this one d is d by dx. See the difference, right? Similarly, if we will apply the same concept and will find x square d square y, that is equals to d minus 1 y. Similarly, x cube d cube y that is equals to d minus 1, d minus 2, y, and so on. Now if you will replace x dy by this dy and x square d square y by this d minus 1 y and x cube d cube y by d minus 1 d minus 2 y in equation number 1, and if you will simplify, then you will get the differential equation of this form, that is function of dy equals to q of e raised to z. Now this is a linear differential equation with constant coefficient, and you can solve this differential equation with the methods discussed with you earlier. Now I will make you understand this concept with the help of examples. Example number 1, solve 4x square d square plus 16xd plus 9y equals to 0. Now you can see that with single derivative we have been given x, and with double derivative we have been given x square. So this differential equation is Euler-Cauchy differential equation. Now to solve this differential equation, let x equals to e raised to z and x dy, that is equals to dy x square d square y, that is equals to d minus 1 y, where this one d, that is equals to d by dz. Here the given differential equation is 4x square d square plus 16xd plus 9 y equals to 0. Now we will replace this x square d square by d minus 1 y. So we have 4 d minus 1, then after plus 16 we will replace this x dy by dy. So we have d only plus 9 y equals to 0. Now we will simplify this one equation, multiplying 4d by d minus 1. So we have 4d square minus 4d plus 16d plus 9 y equals to 0. So we have 4d square 16d minus 4d, that is plus 12d plus 9 y equals to 0. Here this differential equation is of this form, function of dy equals to 0, and its solution is given by taking f of d equals to 0. So f of d equals to 0 and replacing d by m, so we have f of m equals to 0. Here f of d, that is 4d square plus 12d plus 9. Now in this function of d we will just replace d by m. So we have 4m square plus 12m plus 9, that is equals to 0. Now we have to factorize this equation. We have to split the middle term 12m. We have to find out two numbers such that their product is 9 4 are 36 and their addition is 12, and those two numbers are 6 6 are 36 and 6 plus 6 is 12. So we will keep first term 4m square as it is. We will split the middle term 12m as 6m plus 6m plus 9, that is equals to 0. Now taking 2m common from these two terms, so into bracket we have 2m plus 3. Now taking 3 common from these two terms, so into bracket we have 2m plus 3, that is equals to 0. Now again taking 2m plus 3 common, so in one bracket we have 2m plus 3 and in second bracket we have 2m plus 3, that is equals to 0. So we have 2m plus 3 equals to 0, 2m plus 3 equals to 0. So from here we have 2m equals to minus 3, so m equals to minus 3 by 2. So again we have m equals to minus 3 by 2. So in this case the solution is y equals to c1 e raised to minus 3 by 2z. Why we have written z over here? Because d is d by dz. Then after plus sign, as this root is repeated one, we will multiply the result by z. So we have c2z e raised to minus 3 by 2z. So this is equals to c1. We will write down this one as e raised to z the whole raised to minus 3 by 2 plus c2 z e raised to z the whole raised to minus 3 by 2. Now we know that x equals to e raised to z. Therefore, if we will take logarithm both sides, we have z equals to logarithm of x. So in this solution, we will just replace e raised to z by x and z by log x. So finally, the required general solution is y equals to c1 x raised to minus 3 by 2 plus c2 log x raised to minus 3 by 2. Now taking x raised to minus 3 by 2 common, so into bracket c1 plus c2 log x. So y equals to x raised to minus 3 by 2 into bracket c1 plus c2 log x. So this is the required general solution of the given differential equation. Now we will see example 2. Solve x square d square by dx square plus x dy by dx plus y equals to 4 sin log x. Here you can see that with dy by dx we have x and with d square by dx square we have x square. So this is Euler-Cauchy differential equation. To solve this type of differential equation, let x equals to e raised to z and x dy by dx, that is equals to dy x square d square y by dx square, that is equals to d minus 1 y. X equals to e raised to z. Now taking logarithm both sides, we have z equals to logarithm of x. Now the given differential equation is x square d square y by dx square plus x dy by dx plus y equals to 4 sine of log x. Now in this differential equation we will just replace x dy by dx by dy, x square d square by dx square by d minus 1y. So we have d minus 1y plus dy plus y equals to 4 sine. We will replace log x by z. So we have sine z. Now simplifying this expression, multiplying d by d, so we have d square, 1 by d, so we have d, then after plus d plus 1, we have taken y common also, this is equals to 4 sine z. Now minus d plus d will cancel out, we have d square plus 1 y equals to 4 sine z. Now we have to solve this differential equation. d square plus 1 y equals to 4 sine z. Now this differential equation is of the form f of dy equals to, this is function of z, say r of z. Now its solution is given by y equals to cf plus pi. So first of all we will find out cf. So to find cf, we will write down f of d equals to 0. We will replace d by m. So f of m equals to 0. Here f of d is d square plus 1. So in this f of d, we will replace d by m to evaluate f of m. So we have m square plus 1 equals to 0. So we have m square equals to minus 1, and minus 1, that is nothing but I square. So we have m equals to plus minus 1i, and the real part is 0. Here the imaginary part is 1 and the real part is 0. Now based on this complex number, we will write down CF. CF equals to C1 e raised to 0z cos of 1z plus C2 e raised to 0z sine of 1z. But e raised to 0z is 1, so we have C1, no need to write down 1, replacing z by log x, cosine of log x plus C2 e raised to 0z is 1, no need to write down 1, sine replacing z by log x. So this is the required CF. Now we will find out PI. PI is given by this formula, that is PI equals to 1 upon f of d rz. Here f of dy is of the form rz, that's why I have written r of z over here. So 1 upon f of d is d square plus 1, and r of z, that is 4 sine z. Now we will apply case number 2. Whenever we have been given sine of ax plus b, we will replace d square by minus a square. Here the function is in terms of z, so we have been given sine 1z, so definitely the value of a is 1, so we will replace d square by minus 1. But if we replace d square by minus 1, in the denominator you will get 0. So we cannot directly put down the value of d square equals to minus 1. So now what we will do, we will multiply this result by z, and we will differentiate d square plus 1. So 1 over derivative of d square, that is 2d, derivative of 1 is 0, 4 will be as it is, and sine z will be as it is. Now 4 upon 2 is 2, so this is equals to z by 2, 1 upon d sine z. As all of you know that d means derivative, so 1 upon d means integration. So this is equals to z by 2 integration sine z dz. So this is equals to z by 2 integration sine z, that is minus cos z. So this is equals to, now replacing z by log x, we will keep this minus sign outside, divided by 2, cosine of replacing z by log x. So this is the required PI. At last we will write down the general solution, that is y equals to CF plus PI. This is equals to CF is C1 cosine of log x plus C2 sine of log x, and PI is minus log x by 2 cosine of log x. So this is the required general solution of the given differential equation. So in today's lecture we have seen Cauchy-Euler differential equation. We have gone through the standard form of Cauchy-Euler differential equation. We have discussed how to solve the Cauchy-Euler differential equation, and we have gone through 2 examples based on this topic. Thank you for watching this video.